Hello. Look at that. All right. AP Calculus Lecture 4.3, 4.4. So you're going to need to go to Teams. It goes to the File section. I've got a PDF of this thing. Print it out and we will go over it. So now we're getting into Chapter 4 where you're going to actually be doing some practical stuff with this anti-differentiation. So how do you find the area of exotic shapes? This was from our first day lecture. This was the second question of calculus. And today, we're going to answer it. All right? So you approximate the area by dividing the region into rectangles and summing the area of each rectangle, which we did in yesterday's lecture. All right? And as the number of rectangles used to approximate the area increases, the approximation becomes more accurate. The skinnier the rectangle, the better. So if we can divide the region into infinitely many rectangles, as the width delta x approaches 0, okay, the width of that rectangle, delta x, if it approaches 0, you're just getting a line, right? And then there's no error. There's no gap up here at the top. We can determine the exact area of the region by summing all the rectangles. So this big fancy integral symbol, just think of that as a big S. Sum. We're summing. Height times base. All right. The height is f of x. The base is delta x. All right. So the area is equal from A, okay, from A to B. That's how you say it, from A to B. Of f of x dx. We call this a definite integral from A to B. These are the limits of integration. So that's the fundamental theorem of calculus, FTC. It's if f is continuous on the interval A to B and big F is the antiderivative of f, then you take the antiderivative and plug in B and subtract the antiderivative and plug in A, and that will give you the area. All right, so the fundamental theorem of calculus enables you to evaluate definite integrals and empowers you to find the area between a curve and the x-axis. Now there's a second part of the fundamental calculus. We will not get into this very much until we are studying for the AP test. But that's the rate of change of area under the graph of a function with respect to x is the value of that function at x. And in simpler terms, it just means that the derivative and the integral undo each other. Again, we won't be working any problems from the book right now. That's something later in the spring that we'll be doing. All right, we're just going to be doing the fundamental theorem of calculus part 1, which is this today. All right, so now time to work some examples. All right, time to get a better pen. Throw that one away. All right, that one doesn't look very good either. We'll try that one. Okay, let's say we have find the area. Under the curve. For f of x is equal to x. And we want to do this between x equals 0 and x equals 3. Okay, so let's draw this in a graph. F of x equals x. That's just, a line at a 45-degree angle. And this is 0, and this is 3. Okay, so we're just making a triangle, right? So we want to know the area under the curve. Okay, and so the height of this thing would also be 3, right? Since f of x is equal to x. So we know for a triangle, area is equal to 1/2 base times height. So that's 1/2, 3 times 3. which would be 9/2. Okay, but we could use calculus to find this. With most shapes, we don't have a fancy geometry formula, right? So our area is going to be, the way we do it is we integrate from 0 to 3, right? From 0 to 3 of the function x dx. Well, take the antiderivative of x, it's 1/2 x squared. And the way that you write it is then you put a vertical line and put the bottom limit and the top limit from 0 to 3. We're going to plug in 3, 1/2 times 3 squared, and subtract 0. 1/2 times 0 squared. All right. The top limit minus the bottom limit plugged into the antiderivative. And that's going to give you also 9/2. So boom. Fundamental theorem of calculus. Part 1. You just did it. Okay, let's do another one. Okay, our second one is find the area under the curve from 0 to 1 of y is equal to x squared. Okay, so if we were to draw that, and we're just going from 0 to 1, that's a parabola, right? So we would just be looking at that side of a parabola, and let's say that's 1. So we're looking at that area. So we don't have a fancy geometry formula for something like that, do we? Looks kind of like maybe a sail or something. So, but we can figure it out with calculus. So area is going to equal to from 0 to 1 and x squared dx. Take the antiderivative of x squared, that's going to be 1/3 x cubed. And we need to evaluate that from 0 to 1. So that would be 1/3 times plug in 1 minus 1/3 plug in 0. We love 0. Okay, so that is going to be 1/3 times 1 minus 0. It's going to be 1/3. So the area of that little sail, or whatever you want to call it, that shape from 0 to 1 is 1/3. As Isaac would say, neat. All right, next one, find. It's always find the area from 0 to pi. Oh, you know what's coming. Trig. 4. And this is the area under the curve, okay? 4 f of x is equal to sine x. All right, so from 0 to pi. So our area, 0 to pi of sine x dx. All right, what's the antiderivative? Well, it's going to be minus cosine x, right? The derivative of cosine is minus sine. The derivative of negative cosine would be sine. So don't get those messed up. And we go from 0 to pi. So that's going to be minus cosine of pi minus, all right, got to be careful, minus cosine of 0. You really, about around that second one, we need to put a parentheses to make sure we don't mess that up. So what's cosine of pi? It's -1. So that's minus -1 minus cosine of 0 is 1 minus -1. Right, cosine of 0 is 1, you got a minus. All right, that's going to be 1, negative, 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 plus 1, 2. All right, we got a deuce. It's a good Kiss song. Look that up on YouTube. Deuce. From 1975. All right, evaluate. Oh, so it's not find. I'm evaluating. All right, this time we're not gonna say area under the curve. We're just gonna say evaluate this definite integral from -1 to 0 of x minus 2 dx. Okay, let's find the antiderivative of that. That's gonna be 1/2 x squared, that's the antiderivative of x, minus 2x. Now, when you have a definite integral, there's no c, there's no constant of integration. So we don't have to worry about that when we're evaluating it from -1 to 0. Got to be really careful with our signs here. So we've got 1/2 times 0 squared minus 2 times 0 minus, let's put a left parenthesis, 1/2 times -1 squared minus 2 times -1. Close the parenthesis. It's really easy to mess up your signs here. So we have 0 minus, okay, that'd be 1/2 because -1 squared is 1. And then plus 2. So that's 0 minus 2.5 or -5/2. All right, areas can't be negative, but evaluating an integral, a definite integral, can be negative. All right, if it was an area, I'll show you how to fix that in chapter 6, okay? So let's write a warning here. Danger, warning. Be careful of signs when plugging in. I don't know if you can hear my computer give me notifications, but it's actually you guys telling me which homework problems to work from the day before. So I got to look at those in a minute because we're almost through with this lecture. Okay, let me erase. I want to give you one more formula and the homework that goes with this section. You will need to use this formula for number 62. So the average value, it's going to ask you the average value. And this is guaranteed to be on the AP test. So the average value of a function on an interval is given by one over b minus a from a to b, integrate from a to b of f of x dx. So you do just what we did, except you have to multiply the whole answer when you get it by this fraction 1 over b minus a. So you're going to use to work number 62. So here's the homework, page 283, 5, 9, 13, 17, 25 through 37, odd, and then 62. Okay, so we are moving through chapter 4. I think only a couple of more lectures in chapter 4, and I hope you have a good rest of your day.